In this video, we're going to take a look at a concept called differentials. Now, differentials are a little bit of a tricky concept because they're not really real quantities. So in a way, a differential is a useful fiction. So a differential is basically a quantity that looks like this, dx or dy. So dx is a differential, dy is what we call a differential. So they're used, we've seen them before in terms of the derivative. So the derivative dy dx is actually a ratio of two differentials. Now this is a little bit strange, and it's related to why these are fictitious quantities. And that is that the derivative itself is one entity. You can't, for example, cancel out the d's, or you can't do regular algebra with the dy or the dx. This is one cement block of a quantity. So dy dx represents the limit as h goes to 0 of f of x plus h minus f of x over h. You know, you can't separate the dx or the dy. And yet we do so with these differentials, but we have to be careful with how we use them. We also kind of alluded to this sort of thing with the chain rule, where we can say, well, df du times du dx. So df dx is equal to df du times du dx. Essentially, you can think of the du's canceling, even though that's not proper mathematics, because the df du represents one limit, the limit definition of the derivative, whereas du dx represents a different limit, and then those limits have to somehow work together, and yet it can be sort of it can be viewed that way, as though they're canceling out, because it does work. So a differential, if we have a function, so given a function y is equal to f of x, and I've named the independent and dependent variables x and y. So given a function y is equal to f of x, the differentials dx and dy are fictitious, infinitesimally small quantities such that, but they're not arbitrary, they're related by the fact that dy is equal to f prime of x dx. So dy and dx, they're fictitious because you can't really have a quantity that's infinitesimally small. It's as close to 0 as possible without really being 0. So it's basically a useful fiction for us to visualize. So dy is just infinitesimally small, and so is dx, but they're not the same number. They're related to each other so that their ratio is equal to the derivative. So dy is equal to f prime of x times dx. And of course, the way in which they relate to each other depends on the current x value. So dy is equal to f prime of x dx. And of course, if we divide both sides by dx, we get, dy dx is equal to f prime of x. So even though dy dx is its own cement block thing, differentials come into being by doing a little bit of make-believe. Well, what happens if dy and dx are just really small quantities and I kick the dx over to the other side? After all, dy dx can be viewed as the limit as delta x goes to 0 of delta y over delta x. That's really what the limit definition of the derivative is. Your delta x is shrinking to 0, and we're seeing what happens to the ratio of delta y over delta x, and we obtain dy dx. So the dy over dx are what happens to delta y and delta x as both of them go to 0. So the dy and the dx are these fictitious, infinitesimally small quantities whose ratio is equal to the derivative. So you never say, we'll solve for dy, or dy is equal to 3. You can't say that because dy and dx are both infinitesimally small, but it's still proper to have equations such as this that might relate two or more differentials. So dy is f prime of x times dx, which means if I divide through by dx, I get dy dx is equal to f prime of x, which is just the derivative. So let's do an example. Let's suppose that simple function y is equal to e to the 3x. Well, taking the differential dy, so I take the derivative with respect to x, 3e to the 3x times dx, just like that. So this is called the differential. And it is a very useful thing to know because we'll be using this conceptually when we define the definite integral and the indefinite integral, because the dx shows up in the integral sign in calculus 2. And also when we do substitution techniques in calculus 2 with integrals, we'll have a new variable du, and then we'll want to replace a u prime of x dx with the du. So the whole concept of differentials really comes into play when we start to do integration. So right now, basically this is the equation that we get. Differentials are also in a way related to implicit differentiation, because we can also compute differentials of implicit equations. And that might also shed some additional light on what happened here. Basically, we took the derivative of y with respect to y, which is 1, and then we corrected by multiplying by dy. Here we took the derivative with respect to x, which was 3e to the 3x, and then multiplied by the differential dx. So that's sort of what happens when you take the differential of a general implicit equation. So just to review, suppose we have an implicit equation r of x, y is equal to 0. When we differentiate this implicitly, the idea is we might have a term, we'll call it t of x, that depends on x. So that term we differentiate just as normal. We take the derivative with respect to x and we're done. If we have an x squared, it's 2x, end of story, when we differentiate implicitly. This could be a term or a separate factor of one term. So it could be x squared times y squared. When we're using the product rule and we're taking the derivative of the x squared, it's just 2x. Or we might have a second or a different term or a factor, so t, I'll call it s of y. So we may have a factor or a term that depends on y. Now when we differentiate this implicitly, it's s prime of y times dy dx. So this is the chain rule in action. We view y as a secret function of x, so we take the derivative with respect to y first and then multiply by the derivative of y with respect to x. So it's the y derivative times the derivative dy dx. So it happens like that. Now when we, instead of differentiating implicitly, when we take the differential of an implicit equation, something different happens. So if we have an implicit equation like this, and we have one term or a factor that depends on x, when we take the differential, it becomes t prime of x times dx. So we always multiply by a chain rule factor. Basically, taking the differential is like the prime before you actually do the derivative. It's like a indiscriminatory derivative where you're not committing yet to what derivative you're taking. Is it the x derivative or the y derivative? You're just taking the differential, so you don't have to specify what you're differentiating with respect to. Anytime you see any variable, you multiply it by the correcting factor dx or dy. So it's like x is a secret function of an unknown variable. So we differentiate with respect to x, obtaining t prime of x, and then we have to correct by multiplying by the derivative. But instead of doing dx d unknown variable, we don't know what the other variable is. Maybe x is a function of t, dx dt, but we don't know that. We don't know what x might be a function of. So we just say dx. And then we can always, if we want to say it's a derivative with respect to y, we can divide the whole thing by dy. If we want to say it's a derivative with respect to x, we can divide the whole thing by dx. I'll show you what I mean by that in a moment. If I have another term, s of y, the differential is s prime of y times dy. So it's like implicit differentiation. It's the same sort of steps, except no matter what variable you're differentiating at the moment, you always multiply by your chain rule correction factor, and except as a differential, not in a full-blown derivative. It's just dx. Take the derivative with respect to x, multiply it by dx. Take the derivative with respect to y, multiply it by dy. That's what taking the derivative or the differential means. So to do an example, let's consider x cubed plus y cubed is equal to 9. And let's take the differential. Take the differential, or compute the differential. The differential of the entire equation. So we basically start differentiating as normal. And just on the side, it doesn't hurt to remember if we have y as a function of x, dy is equal to f prime of x dx. So we have some notation like this. Okay, so here we have x cubed. So we take the derivative, 3x squared. Since we differentiated with respect to x, we let everybody know by multiplying it by dx. Plus y cubed. Okay, now our term involves y. So let's take the derivative with respect to y. It's 3y squared. 3y squared, and since we took the derivative with respect to y, we need to let everybody know, so we multiply by dy. Derivative of 9 is just 0. So the differential of x cubed plus y cubed is equal to 9 is 3x squared dx plus 3y squared dy is equal to 0. So remember, dx and dy are these fictitious quantities whose ratios equal the derivative. So for example, if you, well, let me just say, this is the differential. So that's the end of it. But you can use the differential to obtain a derivative. So for example, suppose you wanted the x derivative. So this is the differential of, let's call this equation star. This is the differential of equation star. So now suppose you want to take the x derivative. X derivative, so this is implicitly of star. So let's implicitly differentiate star with respect to x. Well, starting from the differential, we just have to divide by the dx. Dx divided by dx is 1. So basically, we divide by dx, divided by dx. The old-fashioned division sign, which I almost never use. In fact, I never use that sign symbol. Let's just do this slash. Divided by dx. That's, who would know that that was a division sign? Okay, you've talked me into it. Divided by dx. And what do we obtain? Dx over dx is 1. We get 3x squared plus 3y squared dy dx is equal to 0. And lo and behold, that's the implicit derivative of equation star with respect to y, right? You would take the derivative of x as normal, 3x squared, plus 3y squared times the correction factor dy dx is equal to 0. So the differential is kind of a non-committal way of taking the derivative, but not with respect to any variable in particular. It's just the differential. And then to get a derivative, an implicit derivative, you go through and divide by the differential of whatever variable you want to differentiate with respect to. In other words, the x derivative, we take the differential and divide the whole thing by a dx. Let's go. Y derivative, we divide the differential by dy. So by dy, it's a little, okay. So y derivative, we divide the differential by dy. So here's the differential, let's divide everything by dy. We get 3x squared dx dy is equal to plus 3y squared dy over dy is 1 is equal to 0. And that's the implicit derivative of star with respect to y. So you see the differential kind of, primes you for taking either derivative you want. It's an uncommitted derivative, So it's the differential of that equation. It's very closely related to the derivative. So it's just kind of a technique. It's not very, like I said, the dx's and dy's are fictitious quantities. But as it turns out, you can do this, and there is kind of an algebra to it. Let's do another example. X cubed y squared plus sine of y is equal to 9. Okay, so here it's a little bit tricky because we have to use the product rule. The differential of this, we have to do first times the derivative of the second plus the second times the derivative of the first. So we get x cubed, derivative of y squared is going to be 2y, and I'm taking the derivative of y squared with respect to y and then correcting by multiplying by the differential dy. So y squared becomes 2y times dy, and then plus the second times the differential of the first. So plus the y squared, the differential of x cubed is 3x squared times the dx, and then the whole thing's equal to 0. So that, oh, there's another term in there. Plus the derivative of sine of y with respect to y is cosine of y, and then we multiply by the differential dy. So it's just like d of sine of y is cosine of y dy. And if you want d by dx of sine of y, you just divide this by dx. If you want d by dz of sine of y, you just divide this by dz. It's just like that. 9 derivative is 0. So that is the differential. It's 2x cubed y times dy plus 3x squared y squared dx plus cosine of y dy. So it's just take the derivative with respect to whatever variable and then multiply by the differential of that variable. So that's the basic technique of doing differentials.